Okay, so hi everyone. Today is our pleasure to have Ruben in. So he's a deep fellow. He's by physics. Previously, he did his PhD in Max Planck for the physics of complex system in Dresden. And I think he joined Deep maybe 2 years ago, right? And today he's talking about some collective behavior, blocking. So let's get started. Thank you.
Thank you, Twan. Great to be here. So I'll be talking about flocking. These are the topics I'll talk about. First, I'll just introduce the microscopic and continuing descriptions of flocking. Then I'll talk about the model that I propose. It's the microscopically reversible theory of flocking. Then I'll briefly talk about some of the related AI project that I've been doing this summer. And then I'll get to the final part where I compute the growth rate, which is the key thing to bring about the flocking transition in for any continuing description of flocking. So flocking, what is it about? Well, this is a phenomenon that started in the 90s. So you see here a flock of birds or a school of fish. They act like a continuum. So people asked, is there maybe a way to describe this as some sort of fluid or something? And the answer is yes. Also, in the Deep seminar has this nice picture on the website. So I'm really at the right place, I think. Can we describe it as a continuum, like fluid, essentially, but it will be slightly different. And what the difference is, I'll discuss later. And at the same time, there's also a microscopic development. So people formulated this microscopic model for flocking. This is the V-check model. And essentially what is happening, it's a very simple model. You have an angle which has a noise term, eta. That's kind of like temperature. So the higher temperature, the larger this noise. And then there's this term which averages over the nearby angles, and then that way they will align just like a flock of birds. They will align their orientation, and you can also have different rules. For example, you can have topological rules where it doesn't matter on the radius, but they'll lead to similar behavior, namely that you can get a flocking transition which depends on the noise. So if the noise is too large, it will not happen. It will just fluctuate too strongly. And if you enhance density, then it will be more robust to this noise, so there will be more flocking. Yes, so people asked, can you formulate a continuum description of flocking? And this is what people came up with. So this is the two equations, which are kind of like the Navier-Stokes equations with some added terms, which I'll get into later. And here you can very simply see how the flocking transition happens, because it will happen when this damping term flips sign, and then you have this homogeneous state where you have a constant velocity magnitude. And a lot of the developments in this equation were related to universal scaling exponents. So there was some sort of fixed point that people believed to be there, but then they changed their mind. There's been a lot of discussion in the community and also numerical simulations to try to figure that out. But now, this year, John Toner wrote a paper which is called The Inconvenient Truth of Flocks, where he essentially says, so John Toner is the one who formulated the Toner 2 equations. He says that you can never know the universal scalings, and that made a lot of people a bit upset. So there was some comment on this work and a reply. So there's a lot of discussion ongoing, and also one thing that was very important is in 2D you have this theory called the Mermin-Wegner theorem, which says that you cannot have long-range order. in 2D, whereas this float transition, it should also work in 2D. And they have some sort of argument to work around that. And that should still hold. It's just that we don't know how these universal scaling exponents precisely what their values are. So that's the current status. So we have the microscopic description and the macroscopic description. But then logical question is, can you go between from one to the other? The way you do that is with kinetic theory. And people did that. They tried to coarse grain the V-check model, or actually in this work in 2006 they coarse grained a V-check-like model. So it's not because it's quite difficult to implement this averaging in kinetic theory because it's a very non-local interaction. And the basic idea is that you have, whereas ordinary kinetic theory, you'd have just a distribution of particles which have all sorts of velocities here, because this V-check model is based on constant velocity magnitude. You only have a distribution of angles, and then you just expand in angular moments. And then the zeroth order, that's just your density equation. The first order, that's your like your momentum balance equation. And that's how you go from the V-check model to the Turner 2 equations. So then there was an alternative work in 2011 by Thomas Ile, which did some clever trick to fully cover this long range alignment term for the V-check.
Can I have a question? So by the Boltzmann distribution, you mean the distribution for the angle theta, right?
Yes.
Why can't they justify the assumption that this distribution should be Boltzmann?
Okay, maybe I should. So I don't mean ordinarily you would have the Maxwell-Boltzmann distribution. Boltzmann distribution, I just meant the distribution of a particle velocity. So whatever this object is that enters your Boltzmann equation. That's all I meant with Boltzmann distribution.
Yeah, but from the simulation of this V-check model, the two equations you introduced at the beginning, it does not seem that the distribution of this theta will be a Boltzmann.
It's not Boltzmann, only it's obtained from a Boltzmann equation for active particles which has a collision kernel. It's a Boltzmann equation, not Boltzmann.
Okay, so it's the Boltzmann equation, not the Boltzmann distribution. Okay,
but he meant that this is distribution. He told the same actually. Because
yeah. So later, this Gaussian distribution, that's the Maxwell-Boltzmann distribution, which actually should be called the Maxwell distribution. So that I'll cover later, but that doesn't apply here because here the velocity magnitude is constant. That's the most essential thing of the V-check model. So this Thomas Ile, he did a Bayer approach where he fully accounted for this alignment effect, but it's a kind of strange paper because this paper does not at all acknowledge that, hardly acknowledge that this paper before exists, even though almost the same method is followed. So also again was a comment and a reply. Recently Kevin Grosvenor, who's here, and Subbu Patil, they followed a different approach, which is based on boost agnostic hydrodynamics, where you don't have these constant velocity magnitudes.
Sorry, Kevin is here?
Online. Yeah, he's in the Philippines.
Yeah. I was surprised too.
So that's kind of the development.
Sorry, but can you say, have they succeeded in obtaining the Turner 2 equations by this coarse graining procedure or not?
Their method.
No, not their method. I mean the papers before that you mentioned.
They also so both of them succeeded. The discussion was about whether in this first work they simplified their microscopic model, so that's like a V-check-like model. And then this paper they claimed that, well, they said, oh, we're just going to do it fully. And then the discussion was about, but it's a toy model anyway, so who cares? And then Don't see said, oh yeah, but it's kind of like moving the goalpost, etc.
So what they found is that they get very specific coefficients for the toner 2 theory, whereas toner 2 is actually more general.
Yeah, sure.
And then when we did, we just sort of realized that there's an influence kernel you could write down even with breathing modes, and then you can get all coefficients if you like. So it's sort of like an effective field theory kind of understand. They got very specific answers. So given a microscopic model, you get some coefficients, which is kind of
Yeah, that's normal.
I feel like Lier model was a bit more generic because it was not a lot of two-body interactions with like high movement.
Just is that if you relax this constant velocity assumption, it's all
So sorry.
if you relax the constant velocity assumption.
Yeah.
Which is different from this model. Does everything that you're going to say change or?
Well, that's what that's what I am going to say. So,
When it's a toy model, you still assume that the birds fly at constant velocity.
so here they assume that, yes. Yeah, so what makes the toner 2 equation so special that they are really different from an ordinary fluid? And why can that arise from the feature model? Well, there are two main ingredients. So one of them is passivity, so activity, which makes it that this alpha term can go negative, whereas a passive fluid can only have this sign. And why that is, it's not too easy to understand it immediately, but I'll explain that throughout the talk. And another ingredient is Galilean invariance, which if you would impose that, all these red terms, they would have to vanish, also some of the ... terms. And this green term, it should be equal to 1. And then you have this Galilean symmetry. And it makes total sense that the toner 2 equations do not obey Galilean invariance because these are birds flying in a medium. So that's the key thing. You have medium effects, which lead to the breaking of Galilean invariance or the breaking of momentum conservation. It's kind of these are sort of two birds.
So the symmetry is broken in the medium. You sort of have an anisotropic medium.
So what I'll be discussing throughout this talk is that there's not really the symmetry breaking comes into play the moment you discard the medium. You sort of say that the medium, we don't pretend that it doesn't exist and they're only the birds. Then you break it because, for example, the birds, they can lose momentum to the air, right? But if you treat everything, then there's momentum conservation, so nothing is broken.
Okay.
It's only when you pretend that the air is not there, it's only the birds, then suddenly momentum is lost. So
The effect of visual comes from the basic terms, basically.
Sure.
But these toner 2 equations are derived when you assume that the speed is constant.
No.
No.
well,
This is ET V0, that, right? The V0, right? I mean.
we need to
So if the gradient of the speed is 0, then you're automatically back into Galilean invariance. Or
So the point is that here we're talking about average velocities, whereas at microscope level these are just microscopic bird velocities. So whatever velocity manifests as an average velocity, that's always averaging over all these. So you can still have a varying average magnitude, right? If you just have it be very incoherent. So yes.
I think the main thing, the way to think about the toner 2 equation is just the further extension. It's not really clear. Just write down anything you want, and if you have Galilean invariance, those coefficients become very specific. If you have there's a wind get something we want.
Yeah. So that's what I just said. There are two ingredients needed. One is a medium, and one is activity or fuel. So first, you need a medium to push off against, but then that's not enough. You need energy to actually perform the flapping of the wings. So these two ingredients are present, and then the question we will ask is, So where does this really come from? Because the V-check model does not really answer this question. So it's kind of implicit in the fact that there's this constant velocity. Or more specifically, we ask the question, where lies the origin of activity in the V-check model? Or just any microscopic description of flocking. These questions, they are related to this phenomenon which I sort of introduced myself, which I call defenestration. So defenestration, it's mainly known from Prague. It happened a lot there. So then it's throwing a person out the window. But you can also throw things out of the window. It's also defenestration. Or you can throw ideas out of the window. And that's this phenomenon that's kind of how active matter always works. You say, oh, well, there's this microscopic fuel consumption. So everything we know about thermodynamics, we sort of throw that out the window and we just simulate at large scales what happens and we try to work backwards. So that's what I try to fight. I try to really see what happens at the microscopic scale. How do you introduce this fuel consuming effect so that things are different from how they would be if there weren't such an effect? That's what I'll try to discuss today. And more generally, so I want to go back to the question, like why was kinetic theory even invented? So in the 19th century, people had all these thermodynamic laws, but they never really understand how it emerged microscopically. And that's how Ludwig Boltzmann, he came into play, and he found this microscopic origin. And so my claim is that although it makes sense that people did this course grading from the V-check model to the thermal equation, because that V-check model is a very popular model that everyone used. It's kind of inconsistent with how the reason why kinetic theory was invented originally, because the whole point is that you find the microscopic origin of physics, whereas the V-check model has all these implicit aspects to it, which you don't really know the origin of. So that's what I'll try to discuss today, and I'll basically consider, I'll formulate this microscopically reversible kinetic theory of flocking. And the basic idea of it is we keep it very simple. So in physics, it's this joke that you treat the cow as a sphere. We will treat birds as sphere, and we will also treat air as sphere. Yeah, so we have spheres, so that's 3 dimensions, where a V-check model is typically 2D. It can also be 3D. But we consider 3D because kinetic theory is actually, when you work with spheres, it's actually slightly easier than working with disks. And it will be microscopically reversible. So microscopic reversibility is something that has been crucial throughout the history of statistical physics. Yeah, the way you could summarize it is as saying that for every individual process, there is a reverse process. It has been important for the H theorem to prove that in a simple way. It's very helpful to have microscopic reversibility. It's tied to detailed balance. It's also crucial for the Onsager relations, which got Onsager the Nobel Prize in chemistry in 1968. And in the 90s, you had this sort of thermodynamics renaissance, which was related to fluctuation theorems, and that was also very much related to microscopic reversibility. So what does this kinetic theory look like? So this is my Boltzmann equation for the birds, which have this 2 collision integrals. One is self, so that's just birds colliding with themselves. That will give rise to the alignment effects that we also study in the V-check model. And then flap, that means you interact with the environment, with the airs, that is. So that's collision with air. And then the air Boltzmann equation is pretty much the same. And you have all these conservation relations for the collision integrals. So you don't want you want to conserve the number of air particles, the number of bird particles. So you have all these conserved moments for the collision integrals.
We clarify, by X you mean the collective position and orientation, no? Because that's what I'm used to.
Yes, so ordinarily, that's a good question. So normally you'd also have a force term, so that will be the gradient of momentum. But we don't have forces, so we only consider hard spheres. So there are no. So this is only a gradient of spatial gradients. Yeah. Yes. So
Just the
velocity.
Just the XT or just the self-proportionality?
There are no self-propulsion speed, so this is just the velocity, yeah, the XDT. Yes. I call this W. That's just the velocity of the air. Yes. So momentum balance. So these collisions with themselves, they individually conserve momentum, right? So this integral itself and this one, they are both zero, whereas here the sum is zero. So the total amount of momentum is conserved of the bird and air. For energy, it's slightly more complicated because again, these individually conserve energy. The bird collision with themselves and the air collision with themselves individually conserve energy.
What is C again?
That's a collision integral. So that's kind of how Boltzmann equation works. You have evolution of the distribution. It is affected by collisions. And that's what this. I'll work out C in more detail later. So here, what we say is that the flapping energy moments, the total is not conserved because we allow for a chemical reaction. So that's a different. We assume that in this medium there are chemicals present which can allow for chemical interactions, and these can violate this conservation. And these chemicals, it's just two of them, which have their own very simple Boltzmann equation, which does not have any spatial evolution.
Sorry, what is the meaning of those chemicals? I mean, talking about flux of birds. What is the meaning?
Well, so birds, they push off against air to get momentum, but that's not enough to actually flap because they also need energy. So this is the fuel that they get.
Okay, so somehow that part is modeling the fuel.
Yeah.
Internal fuel.
Well, I mean, eventually they need to get the fuel externally at some point, right?
Sure, but then they go back somewhere.
That's what. So yeah, that's maybe good. So it's not my intention to have a good description of how birds actually fly. My intention is really to look at the thermodynamic fundamentals to how you can get such a motion with respect to ordinary particles that collide. So I'm always starting from just ordinary spheres. So ordinary spheres, when they collide, there's energy conservation, there's momentum conservation, you get the Navier-Stokes equation. Now I'm really saying, okay, how do we need to depart from that picture to get the Tonen 2 equations? Whereas ordinary people would just say, oh, well, feature model, uniform velocity. So that's the purpose.
But maybe the picture more is an active soup, an active particle in hard spheres that is in a bath with some chemicals in it.
Yeah, but I like to talk about birds.
First, what about wind?
So we have dynamical bird. We have bird particles. This is also a theory of air particles.
Yeah, you could have just a wind.
Yeah. So in principle, what we will get is a two fluid. So essentially two sort of Navier-Stokes-like equations. which interact with each other through a source. For simplicity, we will eventually just turn off the air, we'll freeze it. But if you wanted to, you could model that.
But there is no energy dissipation by just friction in the air and just steering, whatever. So it now looks like that all the energy that's put into the air by flapping the wings can also sort of be transferred back to the birds by inverse collisions, or.
No, so I mean, energy is conserved, right?
But I mean, but it's not really a closed system. I mean, you have your birds flapping around in air, and so they cause turbulence or whatever in the air, and then you lose all this energy to the surrounding, to the heat. I mean, I don't think that, I mean, you have all these birds flapping, and in your system, the birds are able to, you know, get all this energy that they expend flapping back from the air by just, you know.
So there is dissipation. So it's not like it's a I will discuss this later, but so there's no free lunch or so you really need to to activate the system. I'll discuss it later. You really need to steadily input fuel. It's not like you can just add a little bit of fuel and you can just keep on flying with that forever.
But so where is this energy lost then in your equations?
So energy. I mean, yes. Okay. Well, now I'm getting ahead of the talk a bit, but I'll discuss a chemostat, and then that will allow me to drive the system out of equilibrium. That will allow me to display all these effects that are characteristic of activity. If you would sincerely treat all of that and also account for the air evolution, then you would find that constantly there's energy lost from the bird to the air because they are constantly undergoing these reactions. So in principle, that would heat up forever. And then at that point, you'd say, okay, you don't want a system that heats up forever. So we just assume that there's like air everywhere and it will just go very far away and then it will not. So in theory, you will eventually always have some sort of outside system where the energy leaks to. That's correct.
Is this the same as actually imposing a thermostat on the system? Because that would.
Yeah. That would be at that point you would impose a thermostat.
So Ruben, I want to ask why you're focusing on energy there, because I think when we did our analysis, right, we found exactly what you're asking for, which is you get some sort of detailed balance with respect to momentum transfer to the reservoir just from the momentum exchange with the air. So you get this sort of like, whatever the air is doing, your bird will flock towards equilibrium towards that. So that's a term missing in 202, just from allowing for a collision term that can exchange momentum in the reservoir. So I'm saying probably you'll recover that from the momentum, but not necessarily energy.
You recover relaxation.
Yeah. So for us, we get so the idea is you're doing much more than we tried, right? We just sort of looked at momentum violating interactions, a la the stuff by Niels and collaborators. With a collision term, we don't enforce momentum conservation with exchange of the flock. You get additional terms to 202 that look like V minus V equilibrium divided by relaxation time. So the flock co-moves in the air. And if that collision term, and so if you want to model, well, what if the air is doing something crazy, it's moving around, it's moving, well, that's the collision term, right? So it's an external thing that's telling you what the air is doing, which we didn't model, which I think you're about to do. So
yeah.
But for us, it came from that part, the momentum exchange collision.
So there's only one. So this flap term is a collision term that exchanges everything, right? So this will be the energy exchange collision term. It will also be the momentum exchange collision term. That it needs to both be able. The birds need to be able to push off against the air, violate momentum conservation of the birds, and there needs to be activity involved because otherwise you cannot get movement with respect to the air because the dissipation will always push the bird velocity back to the velocities of air. Yes, and so our chemicals, they're very simple. There's two of them. So the amount of reaction that goes from A to B is opposite to the amount of reaction that goes from B to A. So now we describe the collision geometry, assuming these are spheres. So for the collisions with the birds themselves, this is very simple because these are just energy conserving collisions and they follow this rule. So B is the impact parameter, that's the distance from the shortest distance between this line and the sphere center. To count all these collisions, you follow this principle where you just say you have the distribution of one colliding partner with the other one. And then you integrate that over a cylinder that is formed by the relative velocity, that's the length of the cylinder, and the radius is the impact parameter. And then you just integrate over that and you account for all the collisions. Then you can rewrite that. That's very important because the impact parameter is not really what you care about because that doesn't relate to velocities. So you can rewrite that in terms of the scattering angle. And if you do that, it becomes very elegant. It's a simple expression where the vector E prime is the relative orientation of the outgoing relative velocity. So that's how you do it for the spheres themselves. And then from that, you find this collision integral. So where G is the relative velocity magnitude. So this is very simple. This is very well known. But for the and there is one caveat with this, which is something that's still not really solved, I would say, that we had to make the molecular chaos assumption. Because if you would do this rigorously, you would start from the Lier field equation, which treats all the particles properly. And you can derive this BBGY hierarchy, which relates n particle correlation functions with each other. And then you would get a collision integral, which is of this form. So it would relate one particle correlations or distribution with two particle distributions like this. But that will not close your equation. It's like the Boltzmann equation does. So you need to, that's related to the Low-Schmidt paradox, because if you would, so the Lier equation is time reversible, but if you would truncate, so if you truncate like this, then this will introduce the arrow of time into your equations, because now you put the moment before a collision and the moment after a collision, you put them on unequal footing. And that's actually why you can get dissipative effects from the Boltzmann equation, whereas the Lier equation, it's an equation that's fully reversible. So that's kind of a mystery, and there's no sort of rigorous way to take some sort of limit to go from one to the other. So people just take this for granted. But yeah, that's what we will work with. So let's now consider the bird-air collisions. So as mentioned, these will involve a chemical reaction. So this is what it will look like. So if the bird and air collide, they will not change. So they're kind of like catalyzers in this reaction. But the chemical will react. And there will be this energy delta E involved. Because we consider hard spheres, this is a very simple process which can only depend on the impact parameter and the relative velocity magnitude. So we can make it very simple.
I mean, the logic again of the direction is A plus B plus C plus is some.
Yeah, so B, bird, air, and
the C plus.
C plus is the high energy chemical.
Okay.
And it goes to a low energy chemical, and that gives rise to this energy.
I'm also lost now because you actually treat this in terms of hard sphere. So what is actually the role of the C in the hard sphere picture?
Yeah, that's precisely what I. So I just assume that the chemicals, they are sort of ambient, and when the bird and air collide, there might be a chemical present to bring about this reaction, and the probability that this happens is given by this. But yeah, you just assume that they're around and they can bring about this reaction. So yeah, that's the role essentially.
It looks like more like bacteria or active colloids than birds communicating.
Well, yeah.
I'm picturing these spheres with a little battery in them.
Well, I
Carry
mean,
around and
no, but
if you flip against them.
the fuel is around.
Is it a field? You're actually thinking of it as a field?
Yeah. Well, this is
Tracing.
I call it rho, and for simplicity, I don't attribute any dynamics to rho. So rho is like just uniformly distributed.
But you're saying that, you know, you consume one in the interaction and it
Yeah.
transforms C plus into C minus, right?
Yeah.
So they do have some time dynamics somehow.
Yeah, if you would, you could treat all of that if you want to, but I will consider the simple case, which people usually do in active matter, where you just say we have some sort of chemostat, and then in the steady state there will not actually be a depletion of the chemical. It will just be steadily refilled.
Okay.
Yeah, but it's very important. I mean, do you actually think of these chemicals as separate entities, like particles, or do you think of it as a field in the background which could somehow influence these particles? Is that how you actually? I mean,
Yeah,
what's
yes.
the viewpoint, right?
Yeah.
What is the?
Yeah, so we really treat the birth and air as particles, which and that follows from the fact that we have this very specific collision rules. But as far as collision geometry is concerned, the shape of the chemicals or something like that, it does not play a role. We just assume that if the more dense they are, the more likely it is that such a chemical reaction occurs. But we don't say that their shape or something like that matters.
But it's a continuous distribution. of
Uniform,
chemicals.
yes.
Uniform, but it can change. So it is a.
It could change. You could model it.
He's gonna put the chemostat to not change. Yeah.
Yeah.
Yeah. That's what.
But maybe then I'm slightly lost on your general picture, because so we start with the PSEC model, which you say, okay, I don't want to study this because there is this magic energy in the system that I don't like.
Mm-hmm.
And now we're having this background energy, which is some sort of just as magic as the energy in the PSEC model is, or
Well,
do you see this differently?
yeah. So the Vicic model, there is no energy.
Well, there's energy in the sense that these particles move around. They have some sort of magical built-in battery that allows them to move around.
Yeah, well, exactly. But you don't see what happens with momentum. You don't see what happens with energy. That's all implicit. So that's what I'm making now explicit. That you always need a fuel source.
Yeah, but well, maybe what the point is that maybe it's also what they're asking about, that this sort of background energy field that you have is in some sense just as abstract as Egypt model is or not.
Well, I don't think so.
Because there is no interaction with this field.
So there, yeah, it's not a dynamical field. That's true. So, but there is it is interacting with the birds in the air. So in that sense, it's different, and you can. This is a parameter that you. So there's a chemostat. That's what I'll discuss later. You can turn it on, and then that way you can explicitly turn on the activity. So
Yeah,
you can turn it off, and then you have a passive fluid. And if you turn it on sufficiently, you will bring about the flocking transition. So in the Vicic model, there's nothing you can tune so that you can increase the activity so that suddenly there is a flocking transition.
Yeah. So let me just say, the analogy. Okay, it's only an analogy. Is it in active matter? We often use fields, right? So you can use an electric field, or you can use magnetics or anything, right? That actually imposes this activity. I guess that you're talking something like that. That's the analogy. Is that
Yeah.
reasonable?
Yeah.
Because then everything is, I think, on the same page again. When you are using electric field to tune the activity.
Could another way to visualize it is you're coupling a system to multiple reservoirs. One of them you exchange momentum with, maybe energy, and the other one is an internal energy source reservoir. You don't care what they are, you set those in terms that tells you what you can exchange. And that you can model activities.
So multiple reservoirs, you mean air as a reservoir and
For example, so your source of fuel is inside, I mean, you don't need, your equations don't care where that reservoir is, as they know, it's just gas, right? So,
Yes.
to me, the way I understand what you're doing, which I think is
Mhm.
great actually, is that, you know, you're modeling a reservoir for the environment, you're modeling a reservoir for internal fuel source, and you're looking for how an active system can actually interact with them with exchange of everything with both, right? So I think that's,
Mhm.
and you're writing down the collision terms, and you're not being specific about treating them as background, which is what we do all the time.
Yeah. So this is written in terms of U and B because these are the only parameters that matter for a collision, but it's actually easier to work with scattering angle. So we just define a new function because for every B there's a specific scattering angle. And then yeah, so this is maybe the picture. So you have chemicals that are sort of ambient and they have some sort of volume. And if you're within, because this is probability, this is density, so whatever this factor is that is the probability of reaction, it is a volume. And if you're within that volume when that collision takes place, then this chemical reaction can occur. And if it doesn't happen, that's kind of crucial, then the collision does not happen at all. So originally my idea was that then you'd have a passive collision, non-reactive collision, but that's not, then you will never get flocking because you just have too many collisions to ever bring that about because the system really just wants to go to a state where air and birds are aligned. I'll discuss that a bit more later. Yes, so now it becomes a tricky part because we now assume that there is this possibility for collisions to occur where the energy is no longer conserved. And this will give a lot of trouble because all these simple collision rules that I just described, they very much rely on the notion of energy conservation. So when you want to describe your collisions, it's always helpful to decompose your velocities as follows. So you decompose them into a center of mass velocity, capital U, which is always conserved by momentum conservation. And then there is this relative velocity, small u, whose magnitude is determined by energy conservation. But now energy conservation is violated because there is a reaction. And so here a squared is just 2 delta E. So this is proportional to this energy transfer, but it cares also about the what is called the reduced mass of the two particles. And this will make things very tricky because you see it here in this picture. We will assume that when particles collide, because they are ideal spheres, there's only force exerted along the direction that is longitudinal to the line of sphere center, so this line. And from that, you can specify your collision rules in the case when you have energy conservation. The way you do that is you assume that this transverse component, it is invariant, but that's quite tricky because you know the magnitude has changed, as we just discussed. So that will give this equation between this angle between the ingoing relative velocity and the line of sphere centers, and this one, which is the outgoing relative velocity with respect to the line of sphere centers. Then you relate, you find this relation between the scattering angle, which is this angle, this one, and these two psi's. And you also find this relation between the impact parameter and psi. And this is the diameter. That's this distance from these two sphere centers. And that gives you this following equation, which is quite tedious to solve, but I had the help of ChatGPT. So first, one thing that's important to note is that this scattering angle does not work for the full chi domain. which is unlike ordinary collisions.
So, can you repeat what chi is?
That's a scattering angle. So that's the thing you really care about, because the scattering angle, you only want to know what happens to u and u prime, because these are the things that matter for your distribution. And this angle chi is the rotation of the ingoing and the outgoing. Yeah. So the domain is bounded, so not every scattering angle is possible. Whereas for ordinary collisions, there's always, you can get the full domain from 0 to pi. This is the lower bound, because you can see this g only goes to 1, so then that will max it. This is the solution to this problem. And then you can just plug that back in. And you can also, this is very important for microscopic reversibility that we will discuss. There's a relation between the plus g, so that's the g value for the case that there's a collision where the energy goes in, and sorry, where the energy goes out, and the minus g, where the energy goes in. That will come back later. Because now we can really rewrite our flapping collision integral, because previously there was a very simple relation for this b impact parameter in terms of scattering angle, but as you just saw, this is very complicated now. You now need to replace it, and you get the Jacobian term, which is this capital G, which is composed of the small g that I just showed in the following way. And you impose, maybe I should actually stand here. You impose, now to impose microscopic reversibility, you want to say that every forward reaction, there is an equivalent backward reaction. So to impose, ordinarily that's followed automatically, because you count all the collisions that take a state away from what it was, and you count all of them that take it to the state from somewhere else. And there's only one type of collision ordinarily, so that follows automatically. But now you have a forward reaction and backward reaction, and you need to explicitly relate them to each other. So that's what we do now. So now we compute the reverse of this plus, which is now with a minus. And you use this identity, which follows from the one for small g that we just showed, to write this g minus plus in terms of g plus minus. This effect cancels precisely with the effect that you would get from the Jacobian if you would change the measures. That only works in 3D. And then you have this reverse collision rate. And you can then compare this to what you had before. And you see that this is now the same, the measure is the same, so everything is the same except this factor, they are different. And microscopic reversibility means that you then need to impose this for kappa. So this is the reactive volume, which is the volume around this chemical. To bring about this reactive collision, it needs to, the forward and the reverse need to relate in the following way, so that you have microscopic reversibility. So
just a very quick question. So if you go back to the passive case,
yeah,
I guess that becomes trivial, right? So
well, again, in the passive case, A is 0, and G is 1.
Then it's identical.
Yeah.
Important.
Well, so just to clarify, this is actually not technically about passive versus active, because you can have a passive system that's reactive. So the moment it becomes active is only when you turn on the chemostat, which I haven't done yet. So that's maybe a good thing for what I'm about to say. In principle, now all we're just doing is we're putting a set of equations in place so that you could make it active by turning on the chemostat. But for now, this is in principle still a passive system, just a kind of complicated one where you have this reactive collision interplay. Because chemical reactions are not inherently active. It's only when you turn on the chemostat that it becomes active. And to see that, you can look at the H theorem. which only goes to equilibrium when you have a passive state, and you can derive H theorem even for this complicated collision integral. So the way you do that is you consider the H functional of the birds and the air, but also the H functional of the chemicals. Both have this rho log rho term, which is just the standard form that follows from Stirling's approximation. And you want to impose that in equilibrium, the evolution goes to 0. And you want to impose that it always decreases. Yes.
What is the H theorem?
So the H theorem is kind of like the second law of thermodynamics, but it's specific to kinetic theory, and yeah, that's it. So you want, if you show that this decreases, that's because there's this convention with the H functional that is the minus of the entropy. So then
Take sort of
Right.
entropy role.
Yeah, I see what you mean.
Yeah.
It was Boltzmann's attempt to prove the second law, right?
yeah, exactly, yeah.
Okay.
Prove it microscopically. But that's precisely the great mystery of kinetic theory that's related to the what I discussed, the Loach-Schmidt paradox,
yeah.
because in principle you cannot get
Sure.
irreversibility from microscopics.
So here you're requiring it by hand, is that my understanding, or it just follows that?
No. So I've already made the molecular chaos assumption.
Okay, yeah, sure.
So then you can just derive it, which I do. So first, derive the equilibrium state. You just assume that both the bird and air have a Maxwell distribution, and you assume that the chemicals are in a state of detailed balance, and so the plus one is less likely. Yes.
It's really related to my question at the beginning, because what I learned from first year thermodynamics is that Maxwell one distribution for ideal gas, no? But this system definitely very different from ideal gas. So how can you put forward this answer?
Well, so it's important to clarify. So at this stage, there is not yet activity. So
With the activity, it's just identical to ideal gas. Is this statement?
yeah, yes.
Could I just maybe say something else that
Yeah.
not quite what you're saying, but so this has actually been observed in literature for almost a century, right? So if you have a system where you're exchanging momentum with some reservoir, so for example, on a lattice, when you look at phonons, right? And you look at the distribution of things, people have noticed that actually it looks like it's coming from something that's not quite the Boltzmann distribution, but Boltzmann minus V dot P. Right, so it's an additional thermodynamic potential that absorbs factor of, so there is something Maxwell Boltzmann like for one, right? And he's right now considering equilibrium and chase test. He's finding, but it is built in somewhere. So you get the deformation, the Boltzmann weight. So anything you exchange with the reservoir, you get an additional load. And that is at play in
It's
fact.
also the level of Fokker-Planck equation.
Yeah,
When you're
yeah,
external potential, you get a
So anything you exchange with the reservoir, you get an additional potential. And in fact, Gibbs even noticed this, even added the term for angular momentum and so forth. But they've always believed that, this is not a system that breaks kinematic symmetry at the kinematic level only. So therefore they just sort of say, well, you always go to a framework that's not happening. So we're kind of trying to formalize it. But that's what is happening.
Thank you.
yes. So now, so this gets a bit tedious, but to show that it also is decreasing, you just consider. So we only care about the flapping part because the rest is trivial. So we take for the flapping part of the collision integral, we take these evolutions of the H functional. So we take the evolution of distribution, we plug in the collision integral. That all goes in here. And you get these two terms. So this one, it comes from the bird and air, and this one from the chemical. And you can, of course, combine them into a single log, and then you get the following, your integrand has the following form, log x over y times y minus x, which is always negative. And that's actually also how originally the H theorem was proved for the simple case, but in that case you don't did not need the specific interplay between the chemicals and the bird and the air. So it only works when you account for both of these. Yes, so now we've discussed H theorem. I'll take a slide. Yeah, how much time do I have actually?
Half an hour. Less? No.
Half an hour.
No, you asked us, you have us help.
At least I have to read.
So you can speed up. No?
Yeah, I can very quickly go through this. Well, so the idea is, so we have this H theorem, which is a measure of that things change in time irreversibly. And there have been some developments in machine learning where they try to learn this irreversibility. And one of the people who worked on that is Jarzynski, who's one of the greats of the thermodynamics in the 90s, together with Crookes. They use this to apply the Crookes fluctuation theorem to learn certain thermodynamic properties with AI. There have been some other developments. And if you then consider now a much simpler case, hard disk collisions, you also have an H theorem, and you can very easily simulate it. So you just consider 1,000 disks, which have certain collision rules, you initiate them, and you let them evolve. And then here you see, this should have been a GIF on my Adobe, it always works. But this, what happens is the gray line is instantaneous. It will fluctuate quite strongly, but then a running average will just match with this. That follows from the simulation. So if you simulate this goes to the Maxwell distribution. So then you have this sequential data, like 1,000 disks. You run it like 500 times. You have all this data, it's kind of artificial data, but not really, because it's a very chaotic system. And then you can learn this data. So here you have all the velocity input. You want to learn something which has an H, so here we say it must increase in time. So this loss function wants to learn something that increases in time. So it compares the forward time step t plus 1 with t. And then this is a normalization. And this is specifically to make sure that it is punished more strongly for being wrong than it's rewarded for being right. So that's why if it's right, it's only like this. And if it's wrong, it's very strongly affecting the loss. And then we also implement permutation invariance in this model. So we have a model that is a function rho inside a sum of phi inputs, where phi is the same function for every velocity. So all these velocities, they are permutation invariant. And then this is kind of what the model looks like. You consider all these velocity inputs in a permutation invariant way, because they all have the same inputs phi. And then it is all summed, and it goes through a single function rho. And it is then you then compare the time steps. This is also called the Siamese neural network. And then once you've learned it, you need to do a fine fit, because this loss function is specified in such a way that you can never know the right result up to a constant, because it only looks at differences in time. And also you need to add this factor a, because also that it doesn't know. And then you see here, we have here the real H functional, which you can just extract from the input data. And you see that, well, it doesn't fully match, but if you increase the hidden dimension from 16 to 32, it improves very strongly. So this orange line is still quite oscillatory. And then these two red and green lines, they're almost overlapping. So going from 32 to 64 in the hidden dimension does not matter much. Okay, so that was the AI intermezzo.
But it didn't really converge on the real answer.
Yeah.
That's noisy, but it doesn't converge.
That's correct. So yeah.
Why is that?
Well, so the model only learns to be sure about that the whatever input it sees it's the one is later than the other. And the way it wants to learn that is by focusing mostly on on the early times, because the early times, there's the highest amount of dissipation, right? You can see it from the H functional. So it wants to change a lot there, because there it's really certain. Whereas here, there's almost no change. So here it wants to stay completely neutral. So it learns a model that behaves like that. And that's why it's steeper here, just like the ground truth. But we also added the normalization that punishes being too inhomogeneous. So I thought that that's maybe the culprit, but the problem is if you remove that normalization, then everything leads to trouble. So it only makes things worse. So you need to have some sort of normalization to cap the learning that you do. So yeah, I guess that explains why it doesn't go as steep as the real truth. So yeah, that was about the H regional and the AI. So now back to what I was talking about. So this is the chemostat. So that's what I've been talking about throughout. So the chemostat, it means that you now say, okay, this chemical, it's no longer in an equilibrium state, but there's this delta mu which takes it out of equilibrium. And as mentioned, we don't look at dynamics of the chemical in space or something like that. We just assume that throughout uniformly there is an imbalance of the plus and the minus chemical. Then we focus on the simplest term, which is the alpha term, which is both consequence of the fact that there's a medium. It could not be there in the absence of a medium. And also it is a term that can only have the sign that would bring about the flocking transition in the presence of activity. So it's really the most important term for the flocking transition. And the way you get it is, so this is your momentum balance equation that you can derive immediately from the Boltzmann equation. And you just take the moment of this Boltzmann equation with momentum. And then you get this equation where you have this source term. And the source term is because of collision. So ordinarily, when you do kinetic theory, the moment with the collision integral is 0. And that's why you get a Navier-Stokes equation, which does not have a source. But now we say because there's air, this equation is sourced. And you can expand it. So a very crucial thing that we've done here, you said our air and our birds, they have a Gaussian distribution, but their average velocities, which set like the mean of the Gaussians, we assume that they're slightly apart because we know that it will be driven to be very apart, and that's the U0. And then we just expand this flapping integral up to leading order in this U0, and that will give us this alpha term. Ordinarily, so if this alpha would be positive, as it is always the case in a passive case, then this would immediately drive these two distributions back to each other so that they're completely aligned. But now I'll show a case where it can flip if you add enough of the chemostat. Yeah, and very important, so ordinarily in hydrodynamics, you only consider variables which are hydrodynamic variables, meaning variables that are associated with conservation and that are long-lived at long times. And you always discard what people call the gap modes, which in this case would be this U0, because it will always want to go back to this state where the velocities are aligned. So the only reason that we're now still considering this term is because we know that there will be this activation of this term due to the fuel consumption. So this is a very non-standard way of expanding your hydrodynamic theory. Then, so that's, I think, what you said. So in principle, you could, if you want to turn this really into a two fluid where you have the dynamics of bird and air, but we will now just simplify it to arrive at something that is kind of like the Terran 2 equations, where we just say air is completely frozen, and air would allow for me to lose all my energy eventually. And there's only the dynamics of the bird. And then to study this collision integral, let's first consider the very simple case. So we can first just take this energy difference to be 0. That will dramatically simplify everything, because then there's only one kappa, this G Jacobian term that I added, it's now just equal to 1. And you get something that looks like this, and it makes sense that this is the case, because if you don't have any delta E, it's almost as if there was no chemical reaction, right? Because the only way this chemical reaction affects the dynamics is with this energy difference. So what you see here in integrand is all terms that are positive. And the most important one is this one. This is 1 minus cosine the scattering angle. This term is always positive, but it's most positive when chi is equal to pi, which means you have a frontal collision. Right, so two spheres, they go towards each other and a completely reverse course, that's chi equal to pi. But in general, this is always positive when you have a state where there's no energy transfer, no chemical reactions that involve energy transfer. And the frontal collisions, they undermine flocking the most. So they are the most strongly positive. And that's a lesson that we need to account for if we want to bring about this flocking transition, even in the presence of a chemostat, because even in that case, it's almost impossible to get this flocking transition, because these frontal collisions, even when you activate the system, they will just always completely destroy your order. And to better understand this, you can think about it in an ornithological way, because when birds fly, they always position themselves and their wings in such a way that they have very little frontal collisions with air, right? If a bird would fly like this, they would come to a halt very quickly. It will always try to just obtain some lift and have only grazing collisions with air. And that's precisely what we are going to assume for our reactive volume, because as I mentioned, this kappa, it can depend on two things, u and chi. And what we will assume is that only the smallest chi values that are allowed, that only for that it is non-zero. So this theta function, what's going on there is that this term was already the lower bound for chi. That's just allowed by the collision geometry. But now we also say that this together with this is the upper bound. So you always have, you say that only for this very narrow window of scattering angles, a reactive collision takes place. And then you can get this flocking effect. And whereas if you would consider the full scattering angle window, you will never be able to get this sign flip. And then, yeah, so here you see some diagrams. So there are three important parameters in this theory. There's the chemostat, so you need to introduce a lot of activity to bring about this transition. There's temperature, the temperature that sets the distribution of the particles, the Maxwell distribution. And there is the what I call the grazing angle, which you need to be very tiny to only have these grazing collisions with air. And here, yeah, you see precisely what one would expect. So here, if you increase grazing angle, that will make it positive again, whereas the chemostat will make it negative. Here also, if you increase temperature, it will, so if you have it here negative, but then you increase temperature, it will go positive. So temperature, just like in the V-check model, is something that undermines flocking. But it's a very subtle relation, because in the V-check model, temperature is modeled as noise, whereas here temperature is just modeled as the distribution of particles, particle velocities. But the same picture holds. So increasing the grazing angle undermines flocking, increasing temperature undermines flocking, and increasing the chemostat enhances flocking. Yes, that was what I wanted to say. So what did we do? We formulated a microscopically reversible kinetic view flocking that explicitly accounts for the medium, and it uses a chemostat that really activates the system. And we find that the origin of activity lies with destroying or violating detailed balance of the chemical reaction that is involved in the reactive bird-air collisions. To bring about flocking, that's not enough. You need to also look at the mechanics of these collisions and only include the collisions that have very small scattering angle, because if you consider all of them, there will always be frontal collisions which completely undermine your flocking transition. And temperature, we find to play the same role as in the VJIC model, namely that if you make it hotter, then it will be harder to get this long-range odor. Yeah, that's all I wanted to say. Thanks for listening.
Any question for Ruben?
Just a quick clarification. So in the end, you actually have this delta U, which is obviously the potential, but we're talking only about delta E. Are they the same?
No. So the delta E is just the energy that is added when you collide. So that's really microscopic. So you have a forward reaction, and then the outgoing relative velocities, they're modified compared to the ingoing ones, because the energy is not a collisional invariant anymore, and that's measured by delta E. But that can, in principle, the possibility of such collision does not violate the notion of passivity in any way. You could have such a phenomenon where you collide and there's a reaction, and then the chemical energy goes down and the kinetic energy goes up. The statement of activity is then that you say we keep it in a steady state out of equilibrium, where these kind of forward reactions are more likely than their inverse ones, so violation of detailed balance, and that brings about the flocking transition. So that's the difference.
I've been trying to picture these spheres and disks bouncing around. Do you have a video?
Uh,
I would love to see it. Does it look like flocking? I'm trying to imagine, does it actually look like flocking, or is it sort of a...
Yeah, so that's actually one of my also an outlook, yeah. So I wanted to do a numerical simulations, but then I guess I need to go to 2D. So that's what I'm now working on, to really establish this phenomenon numerically.
Why do you have to go to 2D?
You could also do 3D, I guess.
You did one simulation, right? Where you said you had this for the 2D. Right?
Yeah. Well, yeah, that was for the AI internet. So.
Oh, right.
So one thing I didn't understand, a lot of things I didn't understand, but one of them is that actually you only consider the collision between air and bird, right? But never the bird-bird interaction.
Yeah, that's a good point. So the way they still enter the game in a way is by the fact that we started from Maxwell-Boltzmann distributions. So if you don't have bird-bird collisions, then there's no reason for them to have this Maxwell-Boltzmann distribution. So, but they don't play a major role in what I said because they have a collision invariant. So they satisfy momentum conservation. So they will never affect this source, which forms the alpha term, which is the term that brings about the flocking transition. But they're still very important because they essentially enforce the alignment, just like there's this alignment in the VJIC model.
One of the things I'm wondering is that if you modeled one of the particles being bigger than the other one, or did you keep them at the same size? Because of course we know that birds are significantly bigger than air particles.
For this, it does not matter. So here you see a simplified version of this formula, so in this K there are all sorts of constants hidden, including the diameters, and that's the only time it enters this alpha, so that really doesn't matter.
Any other question?
Oh, so did you actually do the course grading? I didn't see that.
Yeah, so okay, I also have a back. So to the extent to which I did coarse graining, it's here, right? So this is the momentum balance equation, coarse grained. So this is all in averages, and then I extracted the source because the source is the alpha. So this is coarse grained. But then the question, so that I have a backup slide about that.
But what is the P there?
P is the stress tensor, conserved stress tensor.
So it can have a lot of terms that you didn't.
Yeah, so that's a good point because you could now ask the question, okay, we have this one alpha term, and this alpha is actually by far the simplest term to compute. Can we get the rest? So 2 points about that. First, there are more terms in term 2 equations which are violating Galilean invariance. These would all have to come from this part because this is fully in accordance with Galilean invariance. So, but here you can also get gradient terms in the end. And the way you could get all those terms, the Galilean invariant and the non-invariant ones.
But you assume Galilean invariance or you did not?
So that's kind of so Galilean invariance, it all depends on it's all in the eye of the beholder. So if you just include both the air and the birds, then you don't even need to talk about that because any violation or seeming violation of Galilean invariance, you know it's just a medium effect. So yeah, so the extent to which I consider the system to be non-Galilean invariant is the extent to which I account for this medium with this source. So I also had one slide. So if you want to really do the full thing, you need to do Chapman-Enskog. And the way you would do that is if you want to get gradient correction, because the source is not a gradient correction, that's very convenient for me. But if you want to get things like viscosity, what you need to do is you expand your distribution to get this phi correction. And this phi is you make an ansatz in terms of all the gradient, possible gradient terms, such as, for example, gradient of velocity. And then what you do is you need to solve the Boltzmann equation iteratively. So that's what you see here. This is the collision term, which depends on this b from this ansatz and will then be proportional to gradient v. But also the left-hand side of the Boltzmann equation will be proportional to gradient v because you assume that it's in local equilibrium. So that will give rise to gradients. So then you get rid of the gradients on both sides, and then you iteratively solve this. But that's incredibly difficult. So even for the simplest case, we're in this book, it's I don't know, 30 pages of computation. But one thing that's important is that all these steps, they are all based on one equilibrium and other conservation, and both of these things, they are no longer there really. So that will pose some additional challenges, but you can consider relaxation time approximation, which is also what Subodh Patil did. So then it would be simplified.
Yeah, I mean, this is going to be a very naive question, obviously. So if I understand correctly, I mean, you need the interaction with air, right, for to make this work. So does that mean that if you're looking for a vacuum, or if you're looking at a flock in space, it cannot be or something like that? There's no flocking in space. This is what conclusion is?
Yes. Yeah.
The birds would be dead.
No. Give them all,
Yeah, you give them spacesuits and they will not be able to flock.
Hard sphere interactions, but he could have started out by relaxing that and having some sort of influence kernel type interaction. It's another dimension you could have pursued.
Yeah.
And probably he'll find his qualitative conclusions go even in that case where you would find flocking in a vacuum.
Well,
the hard sphere approximation that's being disappeared.
Okay.
So
Different interaction.
So what we approached was we just sort of said, what is the sort of, like, if you think about what the V-check model is, like you have a velocity vector, and you form a local mean field somehow, you sort of average over the local direction, and you have a restorative force. So we put that in by hand, and we said we put in different influence columns, and if you put in a top hat, you get certain coefficients for toner 2. If you put in a Yukawa type potential, you get certain things else. You recover the sort of different coefficients that people didn't. Nobody's managed to get arbitrary coefficients, but we managed to do it, and it came into this. But if he decided to do that, he would find flocking. So he's doing something else, which I think is super interesting, right? It's just a different direction that we pursue.
But there is the thing. So the alpha term, I think, in your paper comes from the kinetic mass density equation of state.
Non-conservation of rho.
Yeah.
Non-conservation of rho versus n number. Yes.
Yeah. So, and I think in your you have this final appendix where you derive this from like electro.
So, but remember, we did something very primitive.
Yeah, but even you have this final appendix in this work where you provide a derivation of this term.
It's very good.
And then in that derivation, you start from like a Drude model, right? So
it's completely general.
Yeah, but if you start from that, then this Drude term, it again follows from the fact that electrons, they move in a medium. So
I don't think about it that way, right?
So I do, but there's always you need to always think about.
It's not there, right? So you just have a system, and you're exchanging something with different forces with respect to a reservoir that is taking energy, and so you put in different things, you get different things out. So that was just a heuristic derivation.
Mm-hmm.
We are of course refining it and showing that via a generalized Caldera type formulation, you get now the main problem for us is that we're doing actually kinetic theory derivation with the truncated hierarchy. So for us, at the level at which we calculated, we're not getting anything interesting for alpha, right? Because we have to go higher order and we're lazy. So I think what you're doing is super interesting, but there are crucial ingredients that I would have expected things to appear had you added them. I think the other thing that I'm wondering about is so for us, what we literally did, and it was really like naive, right? You just take kinetic theory and you just start relaxing axioms. For us, that one relaxation was that you have one of the axioms is that the integral of the collision of every conserved quantity is 0. So we drop that one for momentum, and we get toner 2 plus relaxation terms, detailed balance with momentum terms and everything. And then the next one we thought of is there's this H theorem looking around, which doesn't come in at the quadratic order, but it does the cubic order, right? Which means that if you take the collision term and you integrate it with any concave function, that integral is less than 0, and that is basically local conservation of entropy. And for us, we're like, oh wow, probably this is where activity is going to come in. If we start relaxing. Now it seems that you're saying that that's not where activity comes in. That in fact, you can actually keep that thing and somehow still get what looks like activity by still having a local H there. Because I would have thought, any type of chemostatic behavior, eating food, taking things out, is locally producing entropy.
Yeah, no, that is what I'm saying. So yeah, that's maybe a good point to clarify. So I only provided the H stream because I wanted to make the point home that up to the chemostat, this is just a passive system. It's just a very specific engineered passive system, but it's passive, and it obeys the H theorem. H theorem goes to 0, the evolution of the H functional. Everything is as you would expect it, but it's only when you turn on the chemostat that everything changes. And there is, if you then compute the dissipation, there will be steady dissipation. It's out of equilibrium. It's precisely as any active system would be. But it's, I wanted to bring the point home that whereas V-check model, this is all implicit and it's just how it works. You can actually formulate a theory where you start from passive and then you need to turn this thing on, and then it becomes like the toner 2 equations. That really makes the transparent the microscopic origin of activity in the flocking. Thank you.